Hello, everyone, and welcome to the GReTA seminar. Our apologies for a brief delay in the start of the seminar because we are experiencing some technical problems at the Université Paris-Cité, where our website and the servers are located. But it seems, I hope we are we are live now on YouTube and also here in the Zoom meeting, of course. And without further ado, I would like to introduce Davide Castelnovo, who will tell us about new work on M N-adhesivity, and we're very excited to hear about it. So, Davide, thanks a lot. You have the word.
Thank you to you for having me for this talk. And this is a joint work with my supervisor, Marino Miculan and Fabio Verducci. And let's start. Okay. So adhesive categories were introduced by Lack and Sobocinski as a general and abstract framework for the double push-out approach to graph rewriting theory. Roughly speaking, an adhesive category is a category in which push-outs along monomorphisms interact well with certain pullbacks, and well here means in the same way as they do in a topos, in elementary topos. So in this framework, we can prove in an abstract way, in a general way, results such the local charge Rosser theorem or the concurrency theorem. So adhesivity is a property of push-out squares having a mono as one of the two given legs. So we can generalize this notion with two further steps. The first one is M-adhesivity. So M-adhesivity means simply adhesivity, but the one of the legs of the push-out, sorry, comes from a suitable class M of monos. So we are restricting our attention to a subclass of the class of monomorphisms. The other step is restricting even the other leg of a push-out square. And in this sense, we get M N-adhesivity. So we are asking the adhesivity property for squares in which one of the given sides comes from a class M of monos, and the other comes from another suitable class N, not necessarily a subclass of monomorphisms. So what is the formal meaning of push-out that interacts with pullbacks as in a topos? This is given by the notion of Van Kampen square. So we can start with a push-out square, and like the one on the left, and we say that it is Van Kampen if in any cube, like the one on the right, in which the back faces are pullbacks, then the top face is a push-out if and only if the front faces are pullbacks. So this is called Van Kampen property. So we can take a category A, fix a class M of monos and a class N of arrows. And then we have to ask some technical property that I will not bother you about. So some composition and decomposition property, like the class M and N must be closed under composition, etc. And we can give this definition. So we have a category A, Mn as above. We say that A is Mn adhesive if every cospan with a leg in M can be completed to a pullback, and we call this kind of pullbacks M pullbacks. And every span with a leg coming from M and the other leg coming from N can be completed to a push-out, and we call this kind of push-out Mn push-outs. And then we are asking for Mn push-outs to be Van Kampen. So this is the notion of Mn adhesivity. If we take M to be the class of all monos or regular monos, and then to be simply the class of all arrows, we get back the notions of adhesivity or quasi-adhesivity. So we have this result by Lack and Sobocinski, assuring us that this definition of Van Kampen squares is right, because every topos is adhesive. So really, we are capturing a property of topoi. So is there a criterion for deriving Mn adhesivity in a modular way? So how to guarantee that some categorical constructions preserve some adhesivity properties? So in a lot of cases, the proof of M N-adhesivity is given shifting the calculus of pullbacks and pushouts to another category B, whose adhesivity properties are known by other means. And our criterion is just a formalization of this procedure. So let's start with a definition. Take a diagram I from some shape I to C, and take G to be a set, an index set. We say that the family F of functors, a non-empty family F of functors from C into some other DJ, jointly preserve co-limits or limits of I, if given a co-limiting or limiting co-cone or cone for I, then every image through Fj is again co-limiting, limiting or co-limiting. For jointly reflection, the story is the same. We say that a family of functors jointly reflects co-limits if given a co-cone, which is co-limiting for I. If given a co-cone such that every image is co-limiting for the composition, then the starting co-cone is co-limiting for I. For lifting is again the same story. We start with a co-limiting co-cone for every composition. Then we are setting that there exists a co-limiting co-cone for I, such that the image, all the images of it are sent to the same to the starting to the image to the starting co-cones. And finally, we have jointly creation of co-limits, or so limits of co-limits of I, if I has a co-limit and F jointly preserves and reflects co-limits along it. So we are now ready to start to state our criterion. We will fix a category A, some class M and N, and a non-empty family of functors from A into Bj. And we assume that all the Bj's are Mj and J adhesive for some classes Mj and Nj. And we also assume that the images of M and N through any of the Fj are contained into these special classes. So theorem, if every Fj preserves pullbacks and F jointly preserves Mn pushouts and jointly reflects some kind of pushout squares as the one depicted on the right, then Mn pushout squares in A are one company. Moreover, if F satisfies the assumption of point 1 and jointly creates both M pullbacks and N pullbacks, then A is Mn adhesive. Finally, if F jointly creates all pushouts and all pullbacks, then A is MF and F adhesive, where MF and NF are these two classes that you can read on the screen. So basically, we are taking the joint pre-image of all the Mj and J, so the intersection of all the pre-images. So this may seem quite involved, but actually the receipt for this criterion is quite natural. So start with a diagram in A, of which you want to prove a property, apply the functors in F to get a bunch of diagrams in all the Bj's. Now you can use suitable adhesivity properties of the Bj's. And then we can use properties of the family F, like jointly reflection or jointly creation, to recover informations about the starting diagram. So this is, you see, really the formalization of the idea you are computing limits and co-limits as in the Bj's. So let's give some well-known examples. So start with a non-empty family of categories, AI, each of which is Mi and I adhesive. Take their product. Then their product is a Mn adhesive with respect to the component-wise to the class, sorry, given by the product of all the mi and I classes. So this case is proved simply applying our criterion to the family of projections. Again, start with a category A, which is M N-adhesive. Then the functor category, sorry, this should be BA. Clearly, the C should be an A. The functor category, the category of functors from B to A is adhesive with respect to the classes of natural transformations with all components in M and in N. And to see this, just take as F the family of evaluation functors. Finally, if B is M N-adhesive and A is a full subcategory of it closed under full backs, then A is M prime N prime adhesive for every pair of classes that are contained into M and N, respectively, such that A is closed in B under M prime N prime pushouts. And this follows simply applying our criterion to the inclusion functor. So these are the well-known examples, but we have other examples. For instance, the common construction. So what is a comma category? We start with two functors, L and R, with the same codomain. So an object on the comma category L over R is simply an arrow from from L of something into R of something else. And the morphisms of this category are squares, as the one depicted on the right. We have this theorem that is a classic exercise in basic category theory. So if we have a diagram into a comma category, and if L preserves the colimit, if it exists, of UL, of the forgetful functor into A, then the two forgetful functor from the comma into C and the other one into, sorry, must be into A and into B, jointly creates colimits of I. As a corollary, we have that if A and B are M N-adhesive and M prime N prime adhesive category, respectively, and L is a functor that preserves Mn pushouts, and R is a fullback preserving functor, then the comma category L over R is adhesive with respect of the classes given by simply taking the pair of functions of arrows, one coming from M and the other from M prime for the first class, and for the second one, pair of arrows, one coming from N and with a component coming from N, and with second component coming from N prime. So we can apply, we can give other examples. For instance, take the category of simple graphs and the category of directly acyclic simple graphs. We know that these categories are not quasi-adhesive, and thus even not adhesive. But they are both full subcategories of the full category graph of directed graphs, which is a topos, and thus adhesive. So we can try to use our criterion, to apply our criterion to the inclusion functors, and try to prove some adhesivity property for simple graphs and dots. So let's take a monomorphism between two graphs. We say that it is edge reflecting if given an edge between the image of two nodes, then there exists an edge E prime into G between the pre-image of the two nodes, such that the image of that edge is exactly the starting edge. And we say that the mono is downward closed if given an edge with codomain in the image of the starting morphism, then even the edge with which we have begun is in the image of the morphism. So we can characterize edge reflecting monomorphisms as between simple graphs as the regular monos of the category of simple graphs. And now we're ready to state the adhesivity properties of these two categories. So S graph is adhesive with respect to the classes of regular monos that are edge reflecting monomorphisms and of monos, while DAG is adhesive with respect to the classes of downward closed monomorphisms and of general monomorphisms. And the proof in both cases is simply an application of our criterion. We have a full and faithful inclusion in graph, so we only have to check that S graph and DAGs are closed into this category of direct graphs under pullbacks, and that's quite easy, and under the right kind of pushouts. This is a bit longer. It involves some kind of diagram chase. It's a bit lengthy and a bit boring, but it can be done. Now it's pretty easy to do. We can reason about hierarchical graphs. So what is a hierarchical graph? Is a graph in which the set of edges comes equipped with some kind of structure. So formally, we can take the forgetful functor from some category S of structured set into set, and then take the functor R from set to set, which sends X to the product with itself. Then the category of graphs in which the set of edges is an object of S is simply the comma category L over R. From our criterion, it follows that if L is well behaved with respect to certain pushouts, and S has some kind of adhesivity properties, then these adhesivity properties are inherited by the category of hierarchical graphs. We have two examples. The first one is the category S of trees that we can think as a presheaf topos over the poset given by omega by the first infinite ordinal. Then the category of hierarchical graph is adhesive too, because it can be shown that the forgetful functor is colimit preserving. Because basically the forgetful functor means take a presheaf and take the disjoint sum of all the images of every element of omega, of every natural number. Another example, we can take as S the category of directed acyclic graphs. We have just seen that this category has some kind of M N-adhesivity property, in particular when M is the class, an adhesivity property with respect to the class of downward closed monos and all monos. So the category of hierarchical graphs in which the edges are organized as a DAG inherits some this kind of adhesivity. We can replace graphs with hypergraphs. So we can consider two functors. One is the monoid monad, the Kleene star, and the other one is the functor, again, is the functor R as before, in which a set X is sent to the product with itself. If we compose these two, we get a functor R sending a set X to the product of the two free monoid on it. Now, R preserves all connected limits. This is because the monoid monad is Cartesian, so it preserves all connected limits. And this is linked to some logical property of the category of the theory of monoids, but that's not important. So in particular, R preserves all pullbacks. And we can define the category Hype of hypergraphs as the common category given by the identity on one side and this functor R on the other side. So this means simply that an hypergraph is given by a set of hyperedges, a set of nodes, and two functions which assign to every hyperedge a word that is the source and another word that is the target of the hyperedge. We can deduce at once that this category is adhesive. Actually, it can be shown that hype is even a pre-shift topos, but that's not so important. And we can leverage the modularity of our criterion and of the common construction to add hierarchy and interfaces to hypergraphs. So to get a hierarchical hypergraph, we can just replace the identity on set with the forgetful functor from some suitable category of structured sets, exactly as in the case of graphs. Now, to get interfaces are simply given by function from a set X into the set of nodes of an hypergraph. So there is a functor from hypergraphs set which only remembers the nodes of a given hypergraph. And by abstract nonsense, or even by hands, it can be shown that this functor has a left adjoint, delta. So a function from X to the set of nodes is simply a morphism of hypergraphs between the free hypergraph on a set X into a given hypergraph. So the category of hypergraphs with interface is simply the comma category delta over the identity. Therefore, adding interfaces preserves adhesivity because delta is a left adjoint, so preserves all kind of colimits, and the identity is the identity, so it preserves all kinds of limits. Then we have a last example that are term graphs. So we can start with an algebraic signature, sigma. So what is an algebraic signature? It's simply a pair given by a set O of operations and a function R from O into N that assign to each operation an arity. And we can construct the hypergraph G sigma, in which the set of hyperedges is given by the set O of operations, and the set of nodes is the singleton. It's the singleton on V, say. Now the source of operation is simply the word V to the arity of the operation, and while the target of an operation is simply V, because we are thinking about single type algebraic signature. Clearly, there is a coroed version. Then we can take the slice hype sigma over this graph G sigma, and these are simply labeled hypergraphs because giving a morphism between an hypergraph to G sigma is simply giving a morphism between the set of hyperedges and the set of operations respecting the arieties. So we are simply labeling all the edges with the name of an operation. Taking the slice is just a particular instance of the comma construction because it's just the comma construction applied to the identity and the constant functor. And the constant functor preserves all connected limits, in particular pullbacks. So we get the following. This category of labeled hypergraphs is adhesive. This can even be shown saying that the slice of a topos is again a topos. This is a bit of an overkill. So what is a term graph? We start with a labeled hypergraph, L, and it is a term graph if given two hyperedges with the same target, then they must be equal. So if two hyperedges have the same target, then they are equal in the underlying hypergraph. So we have a full subcategory of labeled hypergraphs given by term graphs, and we can apply our criterion to the inclusion factor, just as the case of simple graphs. And we can recover the following theorem. The category of term graphs is quasi-adhesive, because we were able to characterize regular monos in this category of term graphs. So they are basically monomorphisms which send nodes which are not in the image of the target arrow into nodes which are not in the image of the target arrow. And so in this way, you can just explicitly describe pushouts. This result was already known, was proved by Corradini and Gadducci in 2005, but our framework allows us to avoid the traditional direct proof, in some sense, by hand, and to see how instead it relies on general and abstract facts. So the fact that term graphs can be embedded into a topos, but some pushout, but fails to be closed under general pushouts, but it is closed only under some kind of pushouts. And okay, this was the last example. I'm sorry, I was a bit fast. And so to wrap up, we have given a new criterion for M N-adhesivity. This criterion is simply an abstraction from some ad hoc proofs that can be found in literature. Again, all the proofs that are based on the fact that you can compute limits and co-limits in a nice category, and then you can pull back this computation in your static category. This criterion allows us to prove in a uniform and systematic way previous adhesivity results. For instance, for categories built by products, exponents, and comma reconstructions. And for instance, hierarchical hypergraphs and term graphs are built in this way. We have some further work to do. We plan to analyze other categories of graph-like objects, such directed bigraphs and hypernets. For instance, hypernets provide a semantic for monoidal closed category. There is this. Sorry, this year is wrong. It must be 2022. But there is this this paper by Fabio Zanasi, Alvarez Picayo, Dan Gica, and David Sprunger about these hypernets and how they can provide a semantic for monoidal closed categories. They are really hierarchical in nature, and but we don't know if they enjoy some kind of M N-adhesivity properties, and it would be fine to study this kind of stuff. And now this machinery provides a way to prove M N-adhesivity, but it does not provide a guess on the right class M of n of a model. So we have to think about how to verify if the M N-adhesivity properties that we can get from our criterion is suited for modeling specific rewriting systems. For instance, term graph is quasi-adhesive, but in real life applications, this kind of adhesivity properties does not suffice, because you want rules that involves a leg that is a real monomorphism, not a regular one. So, and this machinery is completely mute with respect to this problem. It only allows us to prove an M adhesivity property, but you have to guess which kind of M and then to take. And that's all. So I don't know why LaTeX destroyed the bibliography. sorry, I'm sorry for that. There is a version of this paper published in Fast Proceedings of this year, and there is a longer version with all the computations that you can find on the archive. Really, I'm sorry for this bibliography issue, and I don't know why LaTeX destroyed the bibliography.
Yeah, so thanks, Davide. Very nice. So do we have some first questions? I mean, I have a few, but maybe let the audience go first. Just since you have a few people, just unmute yourself if you have a question.
I was wondering, sorry for joining late. For some reason, I couldn't get to the page with the Zoom link, so we had to sort this out by email. So I was a bit late. I was interested in the last one of the last points there on related work with the bigraphs. So as far as I understand, these are situations. So the bigraphs are basically, I mean, as you say, hierarchical graphs, but they also have interfaces for composing them, right? So and in particular, the bigraphs have interfaces. I mean, basically two sets of interfaces, because you can compose them kind of vertically and horizontally, if you like. So how would you represent that, or does the representation of bigraphs here just extend to the structure but not to the interfaces?
Well, I don't have a definite answer. I mean, you can for sure add interfaces to hierarchical graphs with the same trick, like looking at the forgetful functor, notice that it has a left-hand joint, and in this way you get a single interface. I don't know how to add two interfaces. An idea, a possible idea, is to take to use the functor from the category of errors on set into set given by the codomain, and compose it with the coproduct function, the coproduct functor. So basically, you are getting you are taking two arrows. So you are taking an interface that is x plus y into a set of nodes. So that are basically a two interfaces, and then you can, I don't know, call it one of them inputs and the other one outputs, and that should work. But I didn't work out the details.
I mean, there seems to be a fundamental difference in approach, in a sense, because in all those cases, the bigraphs. And I mean, but you could say the same for the hierarchical graphs, or maybe not the hierarchical graphs, but you could say the same for the term graphs. So they in most of these models are actually the arrows in the category rather than the objects.
Oh,
yeah, so
yes.
Yeah,
but that's a. I mean, that approach is completely different from this one. I mean, because in this one, we are looking at the category in which this kind of graphical, hypergraphical, or hierarchical structures are the objects. If you use them as arrows,
I mean, maybe the usual trick, if that works here, is to use cospans then, but maybe in that sense it's orthogonal. So the question whether they are objects or arrows, because you can move from graphs as objects to graphs as arrows using the cospans.
Yes, exactly.
Then maybe you just focus on representing the actual structure.
Yes.
So maybe I have answered my own question now, but
if you can add, if you can add to this, in fact, you can more or less represent bigraphs as cospans. And of course, the composition is by push out, and you're moving there. To the arrows are from the inner interface, but actually is a cospan of normal morphism between graphs. And there is an old paper by Soboczinski and Sassone, more or less represented this way in the bigraphs.
Okay.
I mean, maybe there is a way to study adhesivity properties of a category in which cospans are arrows. I don't know. I have to think about it.
I don't think they are adhesive because I mean they're completely different. I mean the intuition is completely different there. But maybe modulo I guess the question could be, what are the properties of categories of cospans where the underlying category is adhesive? So that is a question that I guess one could ask, whether there's a generic kind of way of translating the different types of adhesivity into the cospan category. And I think some people have probably done some work on that already, but maybe not using adhesivity, but more basic properties, I expect. Okay.
Thank you for the question.
No, thanks.
Do we have any other questions? So maybe I could ask one. So I found particularly interesting this construction you had for directed acyclic graphs. Yes. So because
yes.
Being an acyclic graph, if I'm not completely mistaken, is a pretty non-local property. No, I mean of a graph to have. So could you say something about? I mean, how could you check then that the push out? I mean, that the sort of, by the way, N is the direction of the rules or of the morphisms you use as matches? Which way around is it?
Yeah, M should be, basically you must have a redex that is a downward closed monomorphisms, and the left leg of the rule, and the right leg of the rule must be a mono.
And so, but I mean, you are still able to prove with your technique that somehow you wouldn't introduce cycles when you
yes.
perform, for example, push out.
Yeah,
or
the point is that if you start with a push out, with a span in which one leg is downward closed and the other is monos, that you can prove, but really by hands, that the resulting push out doesn't have cycles.
And then how would you, because I mean, for rewriting, you might also want to have like compositions of rewriting steps. So would you then have a natural guess for what should be the multisums, like the possible, let's say, if you wanted to do a concurrency theorem or something like that? Is there automatically with your construction included an idea that, sorry, I'm still not clear, M is the matches, I guess. So like the direction.
Yeah, because, okay, but usually I follow the other convention. I mean, in your last paper, you use the opposite convention.
Oh, okay. Sorry. So M is for the rules, N is for the matches.
Yes.
Okay. So I'm asking if with your construction, you automatically know whether it's possible to classify cospans of N through a minimal family. Is that included? Is there some idea?
No, I don't know. Really, I didn't think about it.
Okay, because you're not automatically getting, I forgot that, but I mean, presumably M N-adhesivity, you don't have automatically this efficiency of push-outs of N morphisms, so that you would not.
No, I mean,
that doesn't work.
Our machinery simply, I mean, we simply prove that the push-outs of that kind of spans exist. We didn't even think about the other properties of these push-outs.
Because I mean that could be an interesting step. Although I'm starting to think presumably they could be an effective one to check, but yeah.
Yeah, we simply didn't think about it.
And so that presumably also indicates you haven't really experimented with the actual rewriting you then get out of your nice
No, actually no. I mean, I'm kind of a of a newbie in this world, and I saw this kind of. I mean, I and Marino and Fabio thought about this kind of machinery, but at least I didn't experiment with actual rewriting. Again, this machinery allows you to prove M N-adhesivity properties, but it doesn't suggest if the M N-adhesivity property that you get is useful for your modeling problem. That's a limitation of this technique, because if you have a real life problem, then you have some constraint on the M and N that you want to use and you have to use, and this machinery cannot do anything about this. I mean, if you are lucky, then they write classes work, and if you are unlucky, then you have to think about a way around this problem. And right. it really, this machinery doesn't tell you anything about the structure of the rules.
Sorry, it does tell you, no? Because you're only allowed in M N-adhesivity to take them from M. No?
But for instance, think to term graphs. You want a global conditions on your rules that involves both the L leg and the right leg. And this is not simply one comes from M and one comes from N. It's more, I mean, you have to
usually
look at,
sorry, wouldn't they usually both come from M? If you wanted to really use Eric's style.
Yeah, but for instance, for term graphs, this is not enough. So you want to analyze, I mean, you want how can I say, a more lax approach, because you need more rules. And this machinery
would it be enough if just one of the legs is an M? Or, I mean, what is the exact failure that you're not working in? Both have to be.
I mean,
may I?
Yeah, Fabio.
Yeah, it's quite simple actually. The fact is that usually the rules adopted in term graphs, the left leg has to be mono, not regular mono. Okay, so in order to be sure that the right side push out exists, then you have to impose some condition on the pair left and right. Because just to restrict to regular mono is not enough.
I see.
There are plenty of interesting examples coming from algebraic theories and the implementation of term graphs using algebraic theories where you actually want to be mono. But unfortunately, it's quasi-adhesive, not adhesive.
Right, right. But so because I mean, I was interested in this sort of particular example, sort of. I mean, these directed acyclic graphs, for example. That seems to be a property, being directed acyclic, which is not expressible in first order logic. No, am I wrong?
I don't know. Why not? I mean,
because you seem to be saying something about paths which could in principle be arbitrarily long. I mean, finite, but arbitrarily long.
Yes, you're right.
That's okay.
And so I mean, I'm asking this because it seems to be a very interesting theoretical example where you can illustrate there are data types or like you say, you call them somehow restrictions, I think, of adhesive categories, which you cannot carve out, so to speak, in the calculus of first order conditions and constraints. Because I mean, until your example with the DAX, I had almost the impression that it would be a nice test bed to see, like, for example, a tree is a particular kind of directed graph. So can one express that property in first order logic with constraints and then compare these two approaches? But with DAX, it's funny because it doesn't seem you can express it. I mean, you would presumably need something like MSO.
Well, yes, I don't have a conceptual answer why it works, but it works for DAX. Because really, if you think when to what can go wrong when you take push out, you see that the problem is that you can or send like some kind of a route in a non. I mean, you can violate downward closedness, sending something too much forward in the graphs, or you can identify two nodes. And basically, if you exclude these cases, and the things work simply. And I don't have a conceptual answer why this works, and it would be nice, but in that case, a conceptual answer will be tantamount of a way to systematically guessing which kind of M and N you have to take. And this is because you see, again, you must guess which kind of M and N you have to take before starting with the machinery. And so having a conceptual answer to the problem why with that choice on DAGs works will be tantamount of having a way to identify M and N before applying this machinery. And I don't have an answer to this problem.
All right. Interesting. So do we have any other questions immediately? Raiko, is that a question? Okay, Raiko looked for a moment like a raised hand, but okay. So I would maybe suggest
just eating a sweet.
Oh, okay. Sorry. I must say, unfortunately, we had like I don't know if we were hacked at the University Paris Cité or something, but our servers were down, and so I'm on a very weird setup with a very small screen. So sorry for that. Right. So I would suggest that we thanks the speaker again. Thanks a lot, Davide, for the very nice
talk. Thanks to you for inviting me. Okay.
And I would now stop the YouTube live stream. I see there's quite a few people still on YouTube. So I posted the Zoom link in the chat because apparently our GReTA webpage is down. So if you want to, I mean, on the chat on YouTube also, if you want to join us for the after talk discussion, please do feel free to register. I mean, then you get the Zoom link. And I think the next GReTA talk will be on June 29th by John Barr. So it's an unusual day. It's like our end of season sort of special event. It'll be in the evening and something about interesting stock flow diagrams. So something a bit out of the box. And so with that, thanks again, Davide, and everybody is much invited to stay, of course, online, but I'll stop the live stream now. Thanks a lot. And then you get the Zoom link.